Find a comfortable position. Let your body settle into wherever you are resting right now. Take a slow breath in and let it go. There is nowhere you need to be, nothing you need to do. All you need to do right now is listen, and let the words wash over you like a quiet tide, gentle and unhurried, soft and deep. And as you listen, you might find your eyes growing heavier, your muscles softening, your thoughts beginning to drift like leaves on still water. That is perfectly fine. That is the goal. Let yourself float, and let these facts about one of the universe's oldest and most beautiful forces carry you gently down into sleep. Gravity is the force that holds everything together. It is the invisible hand that pulls the apple from the tree, that keeps your feet on the ground, that holds the moon in its orbit around the earth, and the earth in its orbit around the sun. It is everywhere at all times, never resting, never stopping, never taking a single moment off. And yet, despite being the most familiar force in our everyday lives, gravity remains one of the most mysterious and least understood forces in all of physics. Scientists have studied it for centuries, and still it keeps its deepest secrets close. The story of our modern understanding of gravity begins, famously, with an apple. Or at least that is the legend. Isaac Newton, sitting beneath an apple tree sometime around 1666, watched an apple fall and began to wonder. Not simply why it fell, but why it always fell straight down, why it did not fall sideways or upward, why everything seemed to be pulled toward the center of the earth with such quiet, inevitable consistency. That wondering led to one of the greatest intellectual achievements in human history. Newton formulated his law of universal gravitation, a mathematical description of how every object in the universe with mass attracts every other object with mass. The force between two objects, he said, depends on their masses and the distance between them. The greater the mass, the stronger the pull. The greater the distance, the weaker the pull. It was elegant, it was powerful, and it described the movements of the planets, the tides of the ocean, and the fall of an apple with the same simple equation. Newton's law of gravitation held as the dominant description of gravity for over 200 years. It allowed astronomers to predict the positions of planets with extraordinary precision. It allowed engineers to calculate the trajectories of cannonballs and, later, rockets. It was, by almost any measure, one of the most successful scientific theories ever proposed. And yet Newton himself was troubled by it. He could describe how gravity behaved, he could write the equations, but he could not explain what gravity actually was. How did the Earth reach out across empty space and pull the moon toward it? What was the mechanism? Newton called it action at a distance, and he freely admitted that he did not know how it worked. He wrote famously that he would feign no hypotheses. He described but did not explain. The explanation would wait until 1915, when a young German physicist named Albert Einstein published his general theory of relativity. Einstein's insight was breathtaking in its audacity and its beauty. He proposed that gravity was not a force at all, not in the traditional sense. Instead, he said, gravity is the result of the curvature of space-time. Mass and energy, he showed, warp the fabric of space-time around them, the way a heavy ball placed on a stretched rubber sheet creates a depression, a curve, a dip in the surface. Other objects moving through that curved space-time follow the curves, and we experience that following as gravity. The Earth curves space-time around it, and the Moon, traveling through that curved space-time, follows a path that keeps it in orbit. You are sitting or lying wherever you are right now because the Earth's mass has curved space-time beneath you, and you are simply following the curve. This is a deeply strange and beautiful idea. Space-time is not merely the neutral backdrop against which events unfold. It is a dynamic, flexible, physical thing that can be bent and stretched and rippled. And the bending of space-time is what we call gravity. When you drop a ball, the ball is not being pulled down by a mysterious invisible force. It is following the straightest possible path through curved spacetime, and that path happens to lead toward the center of the Earth. In the language of general relativity, this straightest possible path through curved spacetime is called a geodesic, and all freely falling objects follow geodesics. Let yourself breathe slowly now. In through the nose, out through the mouth. Let your shoulders drop. Let your hands uncurl. Let the weight of your body sink into the surface beneath you, because gravity is doing exactly what it always does, pulling you gently, relentlessly, lovingly toward the center of the Earth, toward stillness, toward rest. The surface gravity of the Earth is approximately 9.8 meters per second squared. This means that if you were to drop an object from rest in a vacuum, with no air resistance, it would be traveling at about 9.8 meters per second after 1 second, about 19.6 meters per second after 2 seconds, about 29.4 meters per second after 3 seconds, and so on, accelerating at a steady, constant rate. This number, 9.8 meters per second squared, is so fundamental to life on Earth that it has its own symbol, the lowercase letter g, and it shows up in physics equations everywhere. It is the heartbeat of terrestrial mechanics, but gravity on other worlds is very different. On the Moon, which is much less massive than the Earth, gravity is only about 1/6 as strong. If you weigh 180 pounds on Earth, you would weigh only about 30 pounds on the Moon. You could jump 6 times as high. Objects would fall more slowly, drifting down with a dreamlike gentleness that astronauts described as both beautiful and disorienting. The Apollo astronauts, walking on the lunar surface, developed a kind of loping, bounding gait because their ordinary walking muscles were far too strong for the weak lunar gravity. They had to learn to move all over again. On Mars, gravity is about 38% of Earth's, a bit stronger than the Moon, but still far weaker than what we are used to. A person weighing 180 pounds on Earth would weigh about 68 pounds on Mars. The surface gravity of Venus is close to Earth's, about 91%, which is one of the reasons Venus is sometimes called Earth's twin. Though in almost every other respect Venus is a hellish nightmare of a world, with surface temperatures hot enough to melt lead and atmospheric pressure 90 times that of Earth's surface. Jupiter, the largest planet in our solar system, has a surface gravity about 2.5 times that of Earth. If you could somehow stand on Jupiter's cloud tops, which you cannot because Jupiter has no solid surface, but if you could, you would weigh 2.5 times your Earth weight. Your heart would have to work much harder to pump blood through your body. Your muscles, evolved for Earth's gravity, would struggle to hold you upright. Extended time in high gravity is physiologically brutal. The Sun has a surface gravity about 28 times that of Earth. A 180-pound person on the Sun's surface would weigh about 5,000 pounds. The pressure on your body would be so immense that you would be crushed flat in an instant. Of course, setting aside the millions of degrees of temperature that would have already turned you to plasma. And then there are the neutron stars, the remnants of massive stars that have ended their lives in supernova explosions. Neutron stars pack roughly the mass of our entire sun into a sphere only about 20 kilometers across, roughly the size of a city. Their surface gravity is so intense as to be almost incomprehensible. It is approximately 200 billion times the surface gravity of Earth. A marshmallow falling onto the surface of a neutron star would hit with the energy of a nuclear bomb. The surface of a neutron star is perfectly smooth on an atomic scale because any mountain more than a few centimeters tall would be immediately pulled flat by the overwhelming gravity. The tallest possible mountain on a neutron star is estimated to be about 5 millimeters high. Let your breathing slow even further now. There is no hurry. The night is long and quiet. The universe is vast and calm. Let the thoughts that have been chattering in your mind begin to grow quieter, like a crowd slowly dispersing, leaving behind only silence and the soft sound of your own breathing. Black holes are perhaps the most extreme expression of gravity in the known universe. They form when massive stars collapse at the end of their lives, concentrating so much mass into such a small region that the resulting gravitational field becomes, in a sense, infinite at the center. The key concept is the event horizon, the boundary around a black hole beyond which nothing, not matter, not light, not any signal of any kind can escape. It is not a physical surface, just a boundary in space, but it is an absolute one. Cross the event horizon and you are committed. You will fall toward the singularity at the center, and nothing in the universe can pull you back. The event horizon of a black hole is sometimes described as the point of no return, and that description is accurate in the most literal possible sense. Once you are inside the event horizon, your future contains the singularity at the center. It is as inevitable as tomorrow. All possible paths through spacetime from your position inside the event horizon lead to the singularity. You cannot avoid it any more than you can avoid moving forward in time. The singularity itself is a point of infinite density, infinite curvature of spacetime, a place where the equations of general relativity break down and cease to give meaningful answers. Physicists believe that a complete theory of quantum gravity, which we do not yet have, would be needed to describe what actually happens at the singularity. It may be that the singularity is not truly a point of infinity, but that general relativity is simply no longer the right tool to describe conditions so extreme. Stephen Hawking showed in the 1970s that black holes are not entirely black. Through a quantum mechanical process now called Hawking radiation, black holes slowly emit energy, very slowly indeed for large black holes, but they do emit. A stellar mass black hole would take an unimaginably long time to evaporate through Hawking radiation, something on the order of 10 to the power of 67 years. For comparison, the current age of the universe is approximately 13.8 billion years, or about 1.38 times 10 to the power of 10 years. So a stellar mass black hole evaporating through Hawking radiation would outlive the current age of the universe by a factor so vast it is nearly impossible to hold in the mind. Supermassive black holes, which lurk at the centers of most large galaxies including our own Milky Way, are even more extreme. The black hole at the center of our galaxy, known as Sagittarius A star, has a mass of about 4 million times that of our Sun. Its event horizon has a radius of about 12 million kilometers. The supermassive black hole at the center of the galaxy M87, the first black hole ever to be directly imaged by the Event Horizon Telescope in 2019, has a mass of about 6.5 billion solar masses. Its event horizon is larger than our entire solar system. Let your body feel heavier now. Let the weight of your limbs sink into the mattress or the cushions or whatever surface is holding you. Feel how the earth is gently, insistently pulling you downward, holding you, cradling you. You do not have to do anything. The gravity is doing it all. Just let yourself be held. Gravity is, in many ways, the weakest of the 4 fundamental forces of nature. The other 3 are the strong nuclear force, which holds atomic nuclei together, the weak nuclear force which governs radioactive decay, and electromagnetism, which governs all electrical and magnetic phenomena. Compared to these forces, gravity is astonishingly feeble. Consider, the electromagnetic force between a proton and an electron is about 10 to the power of 36 times stronger than the gravitational force between them. That is 1 followed by 36 zeros. Gravity is weaker than electromagnetism, by a factor of a trillion. And yet, you are acutely aware of gravity every moment of your life, while you are generally not aware of the strong nuclear force at all. The reason gravity dominates at large scales despite its weakness is that it is always attractive and has an infinite range. The strong nuclear force, while incredibly powerful, only operates over distances smaller than an atomic nucleus. Electromagnetism, while long-range, tends to cancel out at large scales because matter is electrically neutral overall, with positive and negative charges balancing each other out. Gravity, however, has no negative charge. There is no such thing as negative mass. Everything with mass attracts everything else with mass, always with no exceptions, and the effects add up over enormous scales. A planet is made of countless atoms, all of them pulling gravitationally on every other atom in the planet, and on every atom in objects near the planet. Individually, each pull is infinitesimally tiny, but they all add in the same direction, and the cumulative effect is the gravity you feel every moment of your life. This question of why gravity is so much weaker than the other forces is one of the great unsolved problems in physics. It is called the hierarchy problem, and it sits at the heart of much theoretical physics research. Some theories propose that gravity is actually the same strength as the other forces, but that it leaks away into extraspatial dimensions that we cannot perceive, diluting its apparent strength in the three spatial dimensions we experience. These extra dimensions, if they exist, would be curled up at scales far too small to detect with current technology, but they might subtly affect gravity at very short distances. Gravity also plays a central role in the large-scale structure of the universe. In the very early universe, shortly after the Big Bang, the distribution of matter was almost perfectly uniform, but not quite. There were tiny density fluctuations, quantum variations amplified by the rapid expansion of the early universe, regions that were ever so slightly denser than average. Gravity, patient and tireless, began to amplify these tiny differences. The slightly denser regions had slightly stronger gravity, so they attracted more matter, making them denser still, making their gravity stronger still. Over hundreds of millions of years, this process of gravitational collapse and accretion built up the first stars, the first galaxies, and ultimately the vast cosmic web of galaxy clusters and superclusters, threaded by filaments of dark matter and gas that we observe in the universe today. Let your breathing be easy and natural. Let each exhale carry away a little more tension, a little more thought, a little more of the day. You are safe. You are warm. You are held by gravity, gently, always. Dark matter is a substance we have never directly detected, but whose gravitational effects are unmistakable. Observations of the rotation of galaxies show that they spin much faster than they should, given only the visible matter they contain. If only the stars and gas we can see were contributing to galactic gravity, the outer regions of galaxies would spin much more slowly than the inner regions. Similar to how the outer planets of the solar system orbit the sun more slowly than the inner ones. But they do not. Galaxies rotate almost like rigid disks, with their outer regions keeping up with the inner regions. The explanation is that there is much more matter in galaxies than we can see, a vast halo of dark matter surrounding and permeating each galaxy, contributing the gravitational glue that holds the rapid rotation together. Dark matter is estimated to make up about 27% of the total energy content of the universe. Ordinary matter, the stuff of stars and planets and gas clouds and you and everything you have ever touched or seen, makes up only about 5%. The remaining roughly 68% of the universe's energy content is something even stranger called dark energy, a mysterious force that is causing the expansion of the universe to accelerate. Dark energy acts in some respects like an anti-gravity, pushing the universe apart rather than pulling it together. But it is not really the opposite of gravity. It is something new and deeply puzzling, something that does not fit neatly into our current understanding of either gravity or particle physics. The expansion of the universe itself is one of the most profound discoveries in the history of science. In 1929, the astronomer Edwin Hubble published observations showing that distant galaxies are moving away from us, and that more distant galaxies are moving away more rapidly. This was strong evidence that the universe is expanding, that the space between galaxies is stretching, carrying the galaxies apart like dots on the surface of an expanding balloon. If you run the expansion backward in time, all the matter and energy in the universe converges to a single point roughly 13.8 billion years ago, the Big Bang. But in 1998, two independent teams of astronomers studying distant supernovae made a startling discovery. They found that the most distant supernovae were fainter than expected, meaning they were farther away than expected, meaning the universe had been expanding faster in the past than gravitational models predicted. This implied that the expansion of the universe, rather than slowing down under the influence of gravity as had been expected, was actually speeding up. Something was counteracting gravity on cosmic scales, causing the expansion to accelerate. That something is dark energy, and understanding it is one of the deepest challenges in modern cosmology. Breathe deeply. Let the darkness behind your eyelids feel soft and welcoming. There is nothing you need to see right now, nothing you need to watch. Just listen to the words, soft and slow, carrying you gently downward like a leaf settling to the bottom of a still pond. Gravitational waves are ripples in the fabric of spacetime itself, predicted by Einstein's general theory of relativity in 1916, and directly detected for the first time on September 14, 2015, by the Laser Interferometer Gravitational Wave Observatory, known as LIGO. The detection was announced to the world on February 11, 2016, and it was immediately recognized as one of the most significant scientific achievements of the century. Einstein had predicted these waves, but he believed they would be far too weak ever to be detected. For once, he was wrong. Gravitational waves are produced whenever massive objects accelerate. The most powerful gravitational wave sources are mergers of compact objects, things like pairs of black holes spiraling together and merging, or pairs of neutron stars colliding. The September 2015 detection came from the merger of two black holes, one about 36 times the mass of the Sun, the other about 29 times the mass of the Sun, located about 1.3 billion light-years away. As the two black holes spiraled together in their final moments, they radiated an enormous amount of energy as gravitational waves, more power than is radiated as light by all the stars in all the galaxies in the observable universe combined, though only for the fraction of a second of the final inspiral and merger. The resulting merged black hole had a mass of about 62 solar masses. The missing roughly 3 solar masses of energy, equivalent by Einstein's famous equation E equals mc squared to about 6 times 10 to the power of 47 joules, was radiated away as gravitational waves. But by the time these waves reached Earth after traveling 1.3 billion light-years, they had become almost unimaginably faint. The distortion of spacetime they produced was on the order of 1/10,000th the diameter of a proton. LIGO's achievement was to detect a change in the length of its 4-kilometer laser arms by a distance smaller than 1/10,000th of the diameter of a proton. This is, without question, one of the most precise measurements ever made by human beings. Since that first detection, LIGO and its partner observatory Virgo have detected many more gravitational wave events, from both black hole mergers and neutron star mergers. In 2017, the merger of two neutron stars was detected in gravitational waves, and the event was also observed by optical, radio, X-ray, and gamma-ray telescopes around the world, inaugurating the era of what scientists call multi-messenger astronomy, the ability to observe cosmic events through multiple different channels simultaneously. That neutron star merger produced a kilonova, an explosion so energetic that it synthesized enormous quantities of heavy elements including gold and platinum. The gold in any ring you might be wearing was very likely forged in a neutron star collision billions of years ago. Let yourself sink a little deeper now. Your body is heavy and warm. Your breathing is slow. The thoughts that were running through your mind are quieter now, softer, more distant. You are drifting gently, easily into the calm, dark sea of sleep. Tides are one of the most familiar and beautiful manifestations of gravity on Earth. The gravitational pull of the moon on the Earth is not uniform across the planet. The side of the Earth facing the moon is slightly closer to the moon and feels a slightly stronger gravitational pull. The side of the Earth facing away from the moon is slightly farther from the moon and feels a slightly weaker gravitational pull. This difference in gravitational pull across the diameter of the Earth creates tidal forces, which stretch the Earth slightly along the Earth-Moon axis and squeeze it slightly in the perpendicular direction. The Earth's oceans, being fluid and free to flow, respond to these tidal forces more dramatically than the solid rock beneath them. The result is the familiar pattern of two high tides and two low tides each day, as the Earth rotates beneath the tidal bulges in its oceans. The moon is responsible for the majority of the tidal force on Earth, but the sun also contributes, about 46% as much as the moon. When the sun and moon align, at new moon or full moon, their tidal forces add together to produce the higher high tides and lower low tides called spring tides. When the sun and moon are at right angles to each other, at first and third quarter moon, the tidal forces partially cancel, producing the more moderate neap tides. Tidal forces are also responsible for a phenomenon called tidal locking. The tidal forces that the Earth exerts on the moon have, over billions of years, slowed the moon's rotation until it now rotates once per orbit. This means the moon always shows the same face to the Earth. The far side of the moon, which is sometimes misleadingly called the dark side, is never visible from Earth's surface. It is not always dark. In fact, it receives just as much sunlight as the near side over the course of a month, but it is forever turned away from us. We knew nothing of what lay on the far side of the moon until the Soviet Luna 3 spacecraft photographed it in 1959. The images revealed a very different landscape from the near side, with fewer of the large dark plains called Maria and more heavily cratered terrain. Most of the large moons in the solar system are tidally locked to their parent planets. The four large Galilean moons of Jupiter, Io, Europa, Ganymede, and Callisto, are all tidally locked. The large moon Titan is tidally locked to Saturn. Charon, the largest moon of Pluto, is so large relative to Pluto that the two bodies are mutually tidally locked, meaning not only does Charon always show the same face to Pluto, but Pluto always shows the same face to Charon. Io, the innermost of Jupiter's Galilean moons, is the most volcanically active body in the solar system, and gravity is directly responsible. Io orbits very close to Jupiter, and the tidal forces Jupiter exerts on Io are enormous. Moreover, Io is in an orbital resonance with two other moons, Europa and Ganymede. For every 4 times Io completes an orbit, Europa completes exactly 2, and Ganymede completes exactly 1. This resonance keeps Io's orbit slightly elliptical, so the strength of the tidal force Io experiences from Jupiter varies as it orbits. This varying tidal force constantly flexes and kneads Io's interior, generating enormous amounts of heat through friction. This tidal heating powers hundreds of active volcanoes that constantly erupt across Io's surface, making it look, in photographs, like a pizza covered in orange and red and yellow splotches of sulfur and sulfur dioxide. Europa, the next moon out from Io, also experiences tidal heating, though less intensely. This heating is thought to maintain a global ocean of liquid water beneath Europa's icy surface, perhaps 100 kilometers deep. This makes Europa one of the most promising places in the solar system to search for extraterrestrial life. Liquid water, warmth, and chemical gradients at the ocean floor could potentially support living organisms. Your eyelids are so heavy now, so pleasantly, comfortably heavy. There is no need to hold them open any longer. Let them close, or if they are already closed, let them stay closed. Let the darkness be soft and kind. Einstein's general relativity predicted a phenomenon called gravitational time dilation. Time passes more slowly in stronger gravitational fields. This is not a metaphor or an approximation. It is a precise, measured, experimentally confirmed prediction of the theory. Clocks at higher elevations, farther from the Earth's gravitational center, run faster than clocks at lower elevations. The difference is tiny in everyday life, on the order of a few microseconds per day for clocks separated by a kilometer or so in altitude, but it is real and measurable. The GPS satellite system, which you may use every time you navigate somewhere by phone, must account for gravitational time dilation to function correctly. GPS satellites orbit the Earth at an altitude of about 20,200 kilometers. At that altitude, they are farther from Earth's gravitational center, so clocks aboard the satellites run faster than clocks on the ground. They run faster by about 45 microseconds per day due to the weaker gravity at altitude. At the same time, the satellites are also moving at high speed relative to observers on the ground, which according to special relativity causes time dilation in the opposite direction, with moving clocks running slower. The special relativistic effect amounts to about 7 microseconds per day. The net effect is that satellite clocks run faster than ground clocks by about 38 microseconds per day. 38 microseconds per day sounds like nothing, but GPS works by having satellites broadcast their precise positions and the precise times of their signals. Your GPS receiver calculates your position by comparing the arrival times of signals from multiple satellites. An error of 38 microseconds per day, if uncorrected, would cause position errors of about 10 kilometers per day, accumulating over time until the GPS system was useless. Every GPS satellite carries relativistic correction factors, calculated from Einstein's equations, to keep the satellite clocks synchronized with ground clocks. General relativity is not just abstract physics. It is built into the technology that helps you find your way home. Gravitational time dilation becomes extreme near very massive objects. Near the event horizon of a black hole, time dilation becomes effectively infinite. An observer watching someone fall toward a black hole from safely outside would see the infalling person appear to slow down and eventually freeze at the event horizon, their image growing dimmer and redder until it fades into invisibility. From the infalling person's own perspective, however, nothing unusual happens at the event horizon. They cross it without any locally detectable event, and they continue falling toward the singularity. This difference in perspective is one of the most philosophically challenging aspects of black hole physics. To the outside observer, the infalling person never quite crosses the event horizon. To the infalling person, crossing the event horizon is unremarkable. Both perspectives are valid descriptions of the same physical reality, from different reference frames, and reconciling them is a deep ongoing challenge in theoretical physics. Gravitational lensing is another prediction of general relativity that has been dramatically confirmed by observation. Because massive objects curve spacetime, light passing near a massive object follows the curved spacetime, appearing to bend around the object. This bending of light was first observed during the solar eclipse of May 29, 1919, when Arthur Eddington led 2 expeditions to observe the positions of stars near the edge of the eclipsed sun. During a solar eclipse, the sky near the sun is dark enough to see stars, and Eddington's team measured the apparent positions of stars near the sun's edge. They found that the stars appear to be shifted slightly outward from the sun, exactly as Einstein's theory predicted. Because the light from those stars had been deflected slightly inward as it passed near the sun. The amount of deflection was precisely what general relativity predicted, twice the amount Newtonian gravity would have predicted. The announcement of Eddington's results made Einstein world famous overnight. The headline in the New York Times on November 10, 1919, read, "Lights all askew in the heavens. Men of science more or less agog over results of eclipse observations." Since then, gravitational lensing has become an important tool in astronomy. Massive galaxy clusters act as gravitational lenses for even more distant galaxies behind them, distorting their images into arcs and rings and multiple images. By studying the distortions, astronomers can map the distribution of mass in the lensing cluster, including the dark matter that makes up most of the cluster's mass. The most extreme cases of gravitational lensing produce what are called Einstein rings, perfectly circular arcs of light from a distant source that is precisely aligned behind the lensing object. Gravitational lensing can also magnify distant objects, allowing astronomers to study galaxies and stars that would otherwise be too faint to observe. Some of the most distant galaxies ever observed have been detected only because their light was amplified by gravitational lensing. Let your thoughts float further away now. Like clouds drifting across a night sky, drifting and dissolving, leaving behind only darkness and stillness, and the quiet rhythm of your breathing. The concept of escape velocity is one of the most intuitive ways to understand the relationship between gravity and speed. The escape velocity of a celestial body is the minimum speed needed to escape its gravitational pull without any further propulsion. For Earth, the escape velocity is about 11.2 kilometers per second, or roughly 40,000 kilometers per hour. If you could throw a ball at 11.2 kilometers per second, it would never fall back to Earth. It would travel outward forever, gradually slowing but never stopping, asymptotically approaching but never quite reaching a state of rest. For the Moon, the escape velocity is about 2.4 kilometers per second. For Mars, about 5 kilometers per second. For Jupiter, about 60 kilometers per second. For the Sun, about 617 kilometers per second. For a neutron star, the escape velocity can be a significant fraction of the speed of light, perhaps 100,000 to 150,000 kilometers per second, compared to light's speed of about 300,000 kilometers per second. For a black hole, the escape velocity exceeds the speed of light, which is why nothing can escape from inside the event horizon. The event horizon is precisely defined as the surface at which the escape velocity equals the speed of light. Inside that boundary, escape is impossible because nothing can travel faster than light. The escape velocity concept also helps explain why the Earth has the atmosphere it does. The molecules in Earth's upper atmosphere are moving at a range of speeds determined by the temperature. Very light molecules like hydrogen and helium can sometimes reach speeds close to or exceeding Earth's escape velocity, allowing them to escape into space over time. This is why Earth's atmosphere contains very little hydrogen or helium. Heavier molecules like nitrogen and oxygen move more slowly on average and rarely reach escape velocity, which is why our atmosphere consists primarily of nitrogen and oxygen. Mars, with its lower gravity and lower escape velocity of about 5 kilometers per second, has lost most of its original thick atmosphere over billions of years. The gravity on the surface of the Earth varies slightly from place to place. It is strongest at the poles, where you are closest to the center of the Earth due to Earth's slightly flattened shape, and weakest at the equator, where you are both farthest from the center and also experiencing a slight centrifugal effect from Earth's rotation. The difference is small, about 0.5%, but it is measurable. Gravity also varies over the surface due to variations in the density of the rock beneath your feet. Dense rock like iron ore creates slightly stronger gravity. Less dense rock creates slightly weaker gravity. These variations are mapped in extraordinary detail by satellites like the European GOCE mission, producing what is called the geoid, a kind of lumpy theoretical surface where gravity is equal everywhere. The geoid looks vaguely like Earth's shape, but with subtle undulations that reveal the density structure of the rock and ocean water beneath. Your body is so comfortable and heavy now. Your breathing is deep and regular. The world outside is quiet. The night is deep and dark and soft. You are sinking, gently and without effort, into the calm and restful waters of sleep. The first artificial satellite, Sputnik 1, was launched by the Soviet Union on October 4, 1957. It orbited the Earth at an altitude of between 215 and 939 kilometers, completing an orbit in about 96 minutes. Sputnik demonstrated that it was possible to place an object in a stable orbit around the Earth, meaning that it could travel fast enough horizontally that the curve of its falling path matched the curve of the Earth's surface below it. An orbiting satellite is not escaping gravity, it is falling continuously. It just keeps missing the Earth because it is moving sideways so fast that by the time it has fallen a little bit downward, the Earth's surface has curved away by the same amount. A satellite in low Earth orbit is continuously falling and continuously missing. The International Space Station orbits at an altitude of about 400 kilometers and travels at a speed of about 7.7 kilometers per second, completing an orbit in about 90 minutes. The astronauts aboard the ISS are not in zero gravity. They are in free fall. The gravity at 400 kilometers above the Earth's surface is about 90% of the gravity at the surface. The astronauts float because they and the station are all falling together at the same rate, so there is no relative force between them. They are weightless not because gravity is absent, but because they are in continuous freefall. This distinction between weightlessness and absence of gravity is important. Astronauts in orbit are experiencing what Einstein called free fall, the state of following a geodesic through spacetime under the influence of gravity alone, with no other forces acting. Einstein's equivalence principle states that free fall is locally indistinguishable from the absence of gravity. An astronaut floating inside the ISS, with the windows covered, cannot tell by any local experiment whether they are in orbit around Earth or floating in empty space far from any massive object. This principle, that there is no local experiment that can distinguish between free fall in a gravitational field and absence of gravity, was one of the key insights that led Einstein to his general theory of relativity. Extended time in microgravity, as the near-weightless environment aboard the ISS is called, has profound effects on the human body. Without the constant resistance of gravity, bones lose density at a rate of about 1 to 2% per month. Muscles weaken and atrophy. Fluids shift upward in the body, creating the characteristic puffiness in the faces of astronauts in space, and a feeling of persistent nasal congestion. The cardiovascular system, which on Earth must work constantly to pump blood upward against gravity to the brain, partially restructures itself in microgravity, losing some of its pumping capacity. The eyes can be affected too. Intracranial pressure increases in microgravity and can push against the optic nerves, causing visual disturbances in some astronauts. To counteract these effects, ISS astronauts exercise strenuously for about 2 hours every day. Using specially designed resistive exercise equipment that simulates some of the mechanical loading of gravity. Even with this exercise, returning astronauts spend weeks or months readjusting to Earth's gravity, relearning to walk steadily, and allowing their bones and muscles to rebuild. Plans for long-duration human missions to Mars, which would take about 7 months to reach on current propulsion systems, must grapple with the health effects of extended microgravity exposure. One proposed solution is to rotate the spacecraft during the transit, creating artificial gravity through centrifugal force. The required rotation rate would depend on the radius of the rotating section. A rotating section with a radius of about 50 meters would need to rotate at about 4 revolutions per minute to produce an artificial gravity of about 1/3 of Earth's gravity, roughly Mars level. A shorter radius would require a faster rotation, but humans become uncomfortable and disoriented with rotation rates above about 2 to 3 revolutions per minute. Now let your mind be quiet and still. There is nothing you need to think about, nothing you need to solve or plan or remember, just the soft sound of these words, gently carrying you deeper into rest. Let every muscle in your face relax. Let your jaw go soft. Let the muscles around your eyes release. Let your scalp loosen. Let your neck and shoulders be completely at ease. You are safe. You are held. You are at rest. The history of gravity as a scientific concept predates Newton by millennia, though early ideas were quite different from modern understanding. Aristotle believed that heavy objects naturally fell because they were trying to reach their natural place, the center of the Earth, which Aristotle believed was also the center of the universe. In Aristotelian physics, heavier objects fell faster than lighter ones because they had more of the quality of heaviness and were therefore drawn more strongly toward the center. This was a deeply intuitive idea, and it held sway for nearly 2,000 years. Galileo challenged this idea in the late 16th and early 17th centuries. He is famously said to have dropped 2 spheres of different masses from the Leaning Tower of Pisa to demonstrate that they fell at the same rate, though historians debate whether this experiment actually took place. What is not disputed is that Galileo conducted careful experiments with balls rolling down inclined planes, measuring the times and distances, and concluded that in the absence of air resistance, all objects fall at the same rate regardless of their mass. He could not eliminate air resistance entirely, but could minimize it and correct for it. His results directly contradicted Aristotle. This fact that all objects fall at the same rate in a gravitational field, regardless of their mass, is one of the most profound and precisely tested principles in all of physics. It is called the equivalence principle in the weak form. It has been tested to extraordinary precision. Modern experiments using torsion balances and, in space, pairs of falling test masses have confirmed it to better than 1 part in 10 to the power of 15. This means that 2 objects falling side by side in a gravitational field, even if one has a mass 1 trillion times the other, will fall at exactly the same rate to within at least 1 part in 10 to the power of 15. This fact puzzled physicists for centuries. In Newtonian gravity, there are 2 kinds of mass. Inertial mass is the resistance to acceleration, the quantity that appears in Newton's second law, force equals mass times acceleration. Gravitational mass is the quantity that determines how strongly an object attracts and is attracted by other objects. There is no obvious a priori reason why these two quantities should be equal for every object, but experiment after experiment has confirmed that they are, to extraordinary precision. It is this equality of inertial and gravitational mass that explains why all objects fall at the same rate. And it was this equality that Einstein elevated to a fundamental principle in his general theory of relativity. When you think about it in a quiet moment, it is quite remarkable. Drop a feather and a bowling ball in a vacuum and they fall together, side by side, at exactly the same rate. The bowling ball is 1 billion times heavier, but gravity accelerates them identically. This is not an accident or a curious coincidence. It is a deep truth about the nature of spacetime and the equivalence of gravitational and inertial effects. Let your breathing be slow and deep. In through the nose, filling the belly, and out through the mouth, slowly releasing. Each breath taking you deeper into relaxation. Each exhale releasing a little more tension, a little more thought, a little more wakefulness. Orbital mechanics, the mathematical description of how objects orbit other objects under gravity, is one of the most precisely developed areas in all of physics and engineering. Johannes Kepler, working in the early 17th century, discovered that planets move in elliptical orbits with the Sun at one focus of the ellipse. That a line from the Sun to a planet sweeps equal areas in equal times, and that the square of the orbital period of a planet is proportional to the cube of the semi-major axis of its orbit. These three laws, derived entirely from careful observation of planetary positions, were a major step forward in understanding planetary motion. And Newton later showed that they followed directly from his law of universal gravitation. Orbital mechanics is essential for every space mission. To send a spacecraft from Earth to Mars, you cannot just point it at Mars and fire the engines. Mars is moving, the Earth is moving, and the spacecraft will be moving. You need to calculate a trajectory that will take the spacecraft from its departure point to the point where Mars will be when the spacecraft arrives, months later. The most fuel-efficient path is generally a transfer orbit, an elliptical orbit that is tangent to Earth's orbit at its inner end and tangent to Mars's orbit at its outer end. This is called a home and transfer orbit, and a spacecraft traveling it needs no engine burns in between the initial departure burn and the final arrival burn. Gravity does the work. The spacecraft coasts freely through space, following its geodesic, until it reaches Mars. The calculation of such trajectories requires extraordinary precision. A small error in the initial velocity can mean the spacecraft misses Mars by thousands of kilometers. Mission planners use what they call the method of patched conics, treating the spacecraft's trajectory as a series of conical sections, each dominated by the gravity of a different body. The Earth for the departure, the Sun during the interplanetary cruise, and Mars for the arrival. This approximation, while not perfectly accurate, is good enough for initial planning, and more precise numerical integration methods are used to refine the trajectory. Gravity assists, sometimes called gravitational slingshots, are a technique that has allowed spacecraft to travel to the outer solar system with much less fuel than would otherwise be needed. By flying past a planet at precisely the right angle, a spacecraft can steal some of the planet's orbital momentum, gaining speed at the expense of an utterly negligible change in the planet's orbit. The Voyager 1 and Voyager 2 spacecraft, launched in 1977 to explore the outer solar system, used gravity assists at Jupiter and Saturn to gain the speed needed to escape the solar system entirely. Voyager 1 is now the most distant human-made object, traveling through interstellar space billions of kilometers beyond the orbit of the outermost planets. Still in contact with Earth through the Deep Space Network. The Pioneer anomaly, was a mysterious discrepancy in the observed trajectories of the Pioneer 10 and Pioneer 11 spacecraft, which were launched in the early 1970s. As the spacecraft traveled through the outer solar system and beyond, they appeared to be decelerating slightly more than could be explained by known gravitational effects. For decades, this anomalous acceleration was a puzzle. Some physicists proposed exotic explanations involving modified gravity, new physics, or dark matter. Eventually, however, careful analysis showed that the anomaly was caused by the asymmetric emission of thermal radiation from the spacecraft itself. The spacecraft were slightly warmer on one side than the other, due to the orientation of their nuclear power sources. And the momentum of the infrared photons they emitted created a tiny but measurable thrust. When this effect was carefully calculated and accounted for, the Pioneer anomaly disappeared. No new physics required. Let your mind drift now. Let the words become a soft and gentle murmur, carrying you further from the bright, busy world of thought and closer to the dark, quiet world of sleep. You are so comfortable. Your body is heavy and still. The night is peaceful and long. There is all the time in the world for sleep. In 1687, Newton published his masterwork, the Philosophiae Naturalis Principia Mathematica, usually known simply as the Principia. It is generally considered one of the greatest scientific works ever written. In it, Newton laid out his 3 laws of motion and his law of universal gravitation, and then proceeded to derive from these a sweeping array of results: the orbits of the planets, the precession of the equinoxes, the tides of the ocean, the motion of comets, the flattening of the Earth at the poles. It was a tour de force of mathematical physics that had no precedent in human history, and that established the template for how physics would be done for the next 2 centuries. But despite its successes, Newtonian gravity was not perfect. The most famous discrepancy was the precession of the perihelion of Mercury. Mercury, being the closest planet to the Sun, moves fastest and is most sensitive to deviations from pure Newtonian gravity. The perihelion of Mercury, the point in its orbit where it is closest to the Sun, slowly precesses, swinging around the Sun over time. Most of this precession could be explained by the gravitational perturbations of the other planets. But there was a small residual precession of about 43 arcseconds per century that Newtonian gravity could not account for. Various explanations were proposed over the years, including the existence of an undiscovered planet named Vulcan, closer to the Sun than Mercury. No such planet was ever found. When Einstein's general theory of relativity was applied to Mercury's orbit, it predicted exactly the observed 43 arcseconds per century of residual precession. Not approximately, not close, but exactly. This was one of the first great confirmatory tests of general relativity, showing that it corrected Newtonian gravity in precisely the way needed to explain a known observational discrepancy. It must have been an extraordinary feeling for Einstein to see the equations work out. General relativity also predicts the Shapiro delay, a phenomenon in which the travel time of light or radio signals is slightly increased when they pass close to a massive object. This is because the path through curved spacetime near a massive object is slightly longer than the equivalent path through flat spacetime. The Shapiro delay has been measured with high precision by timing radio signals sent to spacecraft and reflected or retransmitted back to Earth. When the signal's path took them close to the Sun, their round-trip travel time increased by a measurable amount, in precise agreement with general relativity's predictions. Let your body relax completely now. Every muscle, every fiber, every cell at rest. Your hands are soft and open. Your face is smooth and peaceful. Your chest rises and falls with each slow, easy breath. You are so close to sleep. Just let yourself go. quantum mechanics and general relativity, are the two great pillars of modern physics, each extraordinarily successful in its own domain. And yet they are fundamentally incompatible with each other in their current forms. Quantum mechanics describes the behavior of matter and energy at the smallest scales, the atomic and subatomic world, with extraordinary precision. General relativity describes gravity and the large-scale structure of the universe with extraordinary precision. But attempts to combine them into a single consistent theory, a theory of quantum gravity, have so far not succeeded. The difficulty is partly mathematical and partly conceptual. In quantum mechanics, quantities like position and momentum cannot be simultaneously defined to arbitrary precision, a consequence of Heisenberg's uncertainty principle. Spacetime itself, in general relativity, is a smooth and continuous structure. But at scales approaching the Planck length, which is about 1.6 times 10 to the negative 35th meters, a quintillion times smaller than a proton. The quantum fluctuations of spacetime should become important, and the smooth spacetime of general relativity should break down. Understanding what happens at these scales requires a theory of quantum gravity. Two of the leading approaches to quantum gravity are string theory and loop quantum gravity. String theory proposes that the fundamental constituents of matter and energy are not point particles, but tiny, one-dimensional vibrating strings, so small that they appear point-like at all accessible scales. Different vibrational modes of the strings correspond to different particles, including the graviton, a hypothetical quantum particle that carries the gravitational force. String theory naturally includes quantum mechanics and also naturally includes gravity, which is one of its most appealing features. However, it requires the existence of extraspatial dimensions and has so far made very few specific predictions that can be tested by current experiments. Loop quantum gravity takes a different approach, proposing that spacetime itself is quantized, made up of discrete chunks rather than being continuous. In loop quantum gravity, space is made of a network of discrete loops called spin foam, and area and volume come in discrete minimum values. Like string theory, loop quantum gravity has not yet made predictions that can be easily tested, but it is an active and mathematically rigorous research program. There is also a model called causal dynamical triangulations, and various approaches inspired by the holographic principle, which suggests that the information content of a volume of space can be described by a theory on the surface of that volume. The most well-developed realization of the holographic principle is the ADS-CFT correspondence, proposed by Juan Maldacena in 1997, which relates a theory of gravity in a space with a certain type of geometry to a quantum field theory without gravity on the boundary of that space. This correspondence has become one of the most productive research tools in theoretical physics, though it has not yet yielded a fully realistic theory of quantum gravity. The search for quantum gravity is one of the deepest and most important open problems in physics. Its resolution would not only reconcile the two great theories of the 20th century, but would likely reveal fundamentally new things about the nature of space, time, and reality itself. You are drifting now, softly, slowly, gently drifting. The words are a lullaby, a soft and steady rhythm carrying you down into the dark, quiet, comfortable depths of sleep. There is nowhere to go, nothing to do, just rest. The cosmic microwave background radiation is the afterglow of the Big Bang, the oldest light in the universe. Emitted when the universe was about 380,000 years old, and the temperature had cooled enough for atoms to form. Before that point, the universe was a hot, dense plasma of protons, electrons, and photons, so dense that light could not travel freely. When the temperature dropped to about 3,000 Kelvin and atoms formed, the universe became transparent, and photons could travel freely for the first time. These photons have been traveling through the universe ever since, and today they constitute the cosmic microwave background, a nearly perfect blackbody spectrum with a temperature of about 2.73 Kelvin, just barely above absolute zero. The cosmic microwave background is extraordinarily uniform across the sky, varying by only about 1 part in 100,000. These tiny variations, mapped in exquisite detail by satellites like COBE, WMAP, and Planck, encode information about the early universe, including the density fluctuation that would grow under gravity into the galaxies and galaxy clusters we see today. The pattern of the temperature variations in the CMB can be analyzed to determine the total amount of matter in the universe, the ratio of ordinary matter to dark matter, the curvature of the universe, the expansion rate of the universe, the age of the universe, and many other cosmological parameters. It is like reading the universe's baby photo. Gravity's role in the formation of cosmic structure from these tiny seed fluctuations is one of the great stories of cosmology. Starting from a nearly featureless early universe, gravity amplified the tiniest density variations over hundreds of millions of years, drawing matter together into the first stars, the first galaxies, and eventually the vast filamentary cosmic web that spans the observable universe. Superclusters of galaxies stretch for hundreds of millions of light years. The Laniakea supercluster, our local supercluster, contains hundreds of thousands of galaxies and spans about 520 million light years. Our own Milky Way galaxy is a relatively minor member of this vast structure. The ultimate fate of the universe depends critically on the balance between gravity and dark energy. If dark energy were not present, the long-term fate of the universe would be determined by whether the total matter density is above or below a critical value. Above the critical value, gravity would eventually halt and reverse the expansion, leading to a big crunch, a collapse of the universe back to a point. Below the critical value, the expansion would continue forever. With dark energy present and accelerating the expansion, it appears that the universe is heading toward an ever-accelerating expansion. Galaxies beyond our local group will eventually recede from us faster than the speed of light, their light redshifted into invisibility, until the observable universe shrinks to just our local group of galaxies, floating in an otherwise empty, cold, expanding void. This eventual fate, sometimes called the Big Freeze or heat death, is a very long way off. The last stars will burn out in hundreds of trillions of years. Black holes will evaporate through Hawking radiation in unimaginably vast timescales. The long, cold, dark future of the universe is remote almost beyond comprehension. But right now, in this moment, gravity is holding the Earth together, holding the atmosphere in place, holding the moon in its orbit, keeping the sun burning, maintaining the structure of the galaxy, and gently but insistently holding you where you are, keeping you close, keeping you grounded, keeping you home. Rest now. Let gravity do what gravity does. Let it hold you. Let it keep you. Let it carry you gently down into the warm, deep, restful darkness of sleep. Your breathing is slow and deep. Your body is heavy and still. The night is quiet and kind. The stars are above you, each one pulled by gravity toward all the others across the vast darkness of space. And you are here, small and warm and safe, resting on this small, beautiful, gravity-bound world. The word gravity comes from the Latin gravitas, meaning weight, heaviness, seriousness. It is related to the Latin gravis, meaning heavy, which is also the root of the English word grief, and of the musical term grave, meaning slow and solemn. There is something fitting about this linguistic family. Gravity is heavy in all senses. It is the weight we feel in our bodies. It is the serious, inexorable pull that keeps us on the ground. It is the slow, solemn force that shapes the universe on its largest scales. And perhaps there is something grave about it, something that invites contemplation, that draws the mind downward and inward, toward the deep and the still. The Latin gravitas was used not just for physical weight, but for moral weight, for dignity, seriousness, substance. A person of gravitas was someone to be respected, someone whose words carried weight, someone not easily tossed about by the winds of fashion or emotion. Gravity, in both the physical and the moral sense, implies a kind of groundedness, a rootedness, a connection to what is real and substantial beneath the surface of things. And there is something deeply grounding about understanding gravity. To know that you are held, that you are not floating free in the dark void of space, but are connected by an invisible web of gravitational attraction to the earth beneath you, to the moon above you, to the sun 93 million miles away, to the supermassive black hole at the center of the galaxy 26,000 light-years distant, to every other object in the universe. To feel that connection, even abstractly, even intellectually, is to feel less alone. Gravity is the universe's way of saying that nothing is truly isolated, nothing is truly alone. Every object with mass reaches out across space and touches every other object with mass. The gravitational pull between you and a star on the far side of the Milky Way is unmeasurably tiny, but it is not zero. You and that star are gravitationally connected. You are part of the same universe, bound together by the same geometry of space-time. The universe, on its largest scales, is a web of gravitational connections, a vast, invisible network of attraction binding galaxies to galaxies, clusters to clusters, superclusters to superclusters. And you are part of that web. Tiny, yes. Ephemeral, yes. But part of it, genuinely and truly part of the universe's gravitational fabric. Let that thought be a comfort as you drift toward sleep. You are held, you are connected, you are part of something vast and ancient and beautiful. Gravity has been shaping the universe for 13.5 billion years, and right now, in this moment, it is doing something very simple and very perfect. It is holding you down and letting you rest. Sleep now. Let gravity do its work. Let the earth hold you. Let the night be quiet. Let your breathing be slow and easy and deep. You are safe. You are held. You are home. The surface of the earth on which you rest has been shaped by gravity over billions of years. The mountains were pushed up by tectonic forces, driven partly by the heat in the earth's interior, and have been worn down by erosion. Driven partly by the motion of water and ice under gravity's pull. The oceans filled their basins because water flows downhill, following the gradient of gravity, finding the lowest points. Rivers carve their valleys because water, under gravity's influence, flows relentlessly toward the sea. The very shape of the land beneath you is a record of gravity's patient, persistent work over eons. Even the roughly spherical shape of the Earth is a consequence of gravity. For a large body, any deviation from a sphere means that some parts of the surface are higher, farther from the center, than others. Gravity pulls those higher parts back toward the center. The result, for any body large enough that its self-gravity overcomes the structural strength of the material, is a rough sphere, deformed only by rotation and by the internal density structure. The threshold size for this to happen is roughly a few hundred kilometers in radius for rocky bodies. Objects smaller than this, like asteroids and small moons, can be irregularly shaped because their gravity is too weak to pull them into spheres. The Earth is not a perfect sphere. It bulges slightly at the equator because of its rotation. The equatorial radius is about 21 kilometers greater than the polar radius. This equatorial bulge means that the Earth's equator is farther from the center than the poles. If you define the summit of a mountain as its distance from the Earth's center, rather than its height above sea level, Then the highest point on Earth is not Mount Everest, but Chimborazo, a volcano in Ecuador near the equator, whose summit is about 6,384 kilometers from Earth's center, compared to Everest's summit at about 6,382 kilometers from Earth's center. Everest is still higher above sea level, at 8,848 meters, compared to Chimborazo's 6,263 meters above sea level. But Chimborazo's position near the equatorial bulge puts it farther from Earth's center. The Earth also has a slight wobble in its rotation, called the Chandler wobble, a small periodic motion of Earth's rotational axis relative to the solid Earth, with an amplitude of about 9 meters at the poles and a period of about 433 days. This wobble is driven partly by the redistribution of mass due to ocean currents, atmospheric pressure variations, and other processes. It is one of many small but measurable ways in which the Earth is not a perfectly rigid, perfectly symmetric, smoothly rotating sphere. Just let those thoughts wash over you. There is no need to remember any of this, no test, no quiz. Just let the words be soft and quiet and carry you along. Your eyes are closed. Your breathing is deep. The room is still. Precession is a slow, gyroscopic wobble of the Earth's rotational axis, caused by the gravitational torques of the Sun and Moon, acting on Earth's equatorial bulge. Over a period of about 25,772 years, Earth's rotational axis traces a slow circle on the sky, like the wobble of a spinning top that is winding down. This means that the celestial pole, the point in the sky around which all the stars appear to rotate, slowly changes over millennia. Today, the North Celestial Pole is near the star Polaris, which is therefore our pole star. But about 13,000 years ago, the celestial pole was near the star Vega, one of the brightest stars in the night sky. In about 12,000 years, Vega will again be the pole star. Precession also means that the vernal equinox, the point in Earth's orbit where the ecliptic crosses the celestial equator, and where the Sun appears to be located on the first day of spring, slowly moves against the background of stars. The constellations of the zodiac, named by ancient astronomers for the constellations through which the Sun passed at various times of year, have drifted significantly from their original positions due to precession. The Sun is no longer in the constellation of Aries at the vernal equinox. It is now in Pisces, and in a few hundred years will move into Aquarius, which is what people mean when they say, "We are entering the age of Aquarius." Ancient astronomers, including the Greek astronomer Hipparchus in the 2nd century BC, noticed the phenomenon of precession by comparing star positions with earlier records. It was one of the first observed effects of the gravitational influence of the Moon and Sun on Earth's shape. Newton later showed that it followed directly from his law of universal gravitation. You are nearly asleep now. I can hear it in your breathing, slow and steady. Your mind is quiet. Your body is at peace. Just a little further down, just a little deeper, into the soft and welcoming darkness, the Moon is slowly moving away from the Earth. The same tidal forces that have locked the Moon's rotation to its orbital period are also, very slowly, changing the Moon's orbit. As the Earth rotates, and the tidal bulge it raises in the ocean sweeps ahead of the Moon due to the Earth's faster rotation, the bulge exerts a slight forward gravitational pull on the Moon, giving it a tiny amount of extra energy that pushes it slightly further out. The Moon is currently receding from the Earth at a rate of about 3.8 centimeters per year, a rate confirmed by laser ranging experiments using retroreflectors placed on the Moon's surface by the Apollo astronauts. At the same time, the Earth's rotation is very slowly slowing down because the energy is being transferred from Earth's spin to the Moon's orbital motion. The length of the day is increasing by about 1.4 milliseconds per century. billions of years in the future. If the sun does not first expand into a red giant and engulf the inner solar system, the Earth and the Moon will eventually become mutually tidally locked, with the Earth always showing the same face to the Moon, just as the Moon now always shows the same face to the Earth. The day and the month will be the same length. But this equilibrium, if it were ever reached, would be short-lived on cosmic timescales, because by that point the sun will be a different kind of star, and its changing gravitational influence will disrupt the delicate balance. The sun, our nearest star, is also very slowly changing. It is converting hydrogen into helium in its core through nuclear fusion, and as helium accumulates, the sun gradually grows slightly brighter and larger. Over billions of years, this brightening will make Earth's surface increasingly warm. In about 1 billion years, the sun will be bright enough to begin a runaway greenhouse effect on Earth, boiling away the oceans and leaving the surface a dry, scorched desert. In about 5 billion years, the sun will exhaust its hydrogen fuel and expand into a red giant, possibly large enough to engulf the Earth's orbit. It will then shed its outer layers as a planetary nebula, leaving behind a white dwarf, a slowly cooling stellar remnant about the size of the Earth, but still retaining about half the sun's current mass. These are the consequences of stellar gravity, the slow, inevitable force that drives the life cycles of stars. Stars form when large clouds of gas and dust in interstellar space begin to collapse under their own gravity. As the cloud collapses, it heats up because the gravitational potential energy of the material is converted to kinetic energy and then to thermal energy. Eventually, if the cloud is massive enough, the temperature and pressure at the center become high enough to ignite nuclear fusion, and a star is born. The star then achieves a kind of balance, called hydrostatic equilibrium, between the inward pull of gravity and the outward pressure of the hot gas and radiation from the nuclear burning in the core. This balance is what defines a star's stable lifetime on the main sequence. When the fuel runs out, the balance is broken. Without the outward pressure of nuclear burning, gravity wins. What happens next depends on the star's mass. Stars of roughly solar mass shed their outer layers gently and leave behind a white dwarf. Stars several times the mass of the sun undergo more catastrophic collapses, with the core imploding in less than a second, as electrons are forced to combine with protons to form neutrons, releasing an enormous flood of neutrinos and causing the outer layers to be blasted off in a supernova explosion. If the remaining core is between about 1.4 and 3 solar masses, it is left as a neutron star. If it is more massive than about 3 solar masses, nothing can stop the gravitational collapse, and a black hole forms. The interplay between gravity and nuclear burning governs the entire life cycle of stars. From the first flicker of hydrogen burning in a newly formed protostar to the final implosion of a massive stellar core. Gravity is the architect of the cosmos. It shaped the first stars, built the first galaxies, drew together the clusters and superclusters, and will ultimately determine the fate of the universe. Rest now. Let all of this settle gently into the background of your mind, soft and quiet like the light of distant stars on a cloudless night. You are here. You are safe. Gravity is doing what it has always done, holding everything together, holding you, holding the world, holding the cosmos in its vast and patient embrace. Let your last waking thoughts be gentle ones. Let them be of the feeling of lying still and being held. Let them be of the simplest, most familiar experience of gravity, the weight of your body pressing softly against the surface beneath you, the ease of not having to do anything to stay here, the deep, animal comfort of being grounded and supported and at rest. Gravity needs nothing from you. It asks nothing. It simply holds. And now, as the words grow quieter and the world grows darker, and your breathing grows slower and deeper and steadier and more even, let yourself be carried down. Down into sleep, down into the quiet, down into the warm and restful and gravity-held darkness, where your body can heal, and your mind can rest, and the whole beautiful, gravity-shaped universe can go on turning without you for a little while, and you can simply be still, and sleep, and dream and rest, held safe on this small and spinning world by the most ancient and universal force there is. Good night, sleep well, you are held. But let us stay here a little longer, in this quiet space between wakefulness and sleep, because there is still so much to explore, so many gentle, fascinating, softly spoken truths about this most fundamental of forces. So settle deeper into your pillow, let your breathing slow another notch, and let the words carry you a little further along the edge of sleep, into the calm and starlit territory of almost dreaming. Gravity is unique among the four fundamental forces, in that it is the only one that has never been successfully unified with quantum mechanics. Electromagnetism was unified with the weak nuclear force in the 1960s and 1970s, producing what is called the electroweak theory. Grand unified theories attempt to also incorporate the strong nuclear force, but gravity resists unification. It stands apart, described by a completely different mathematical framework from the quantum field theories that describe the other forces. This is not merely a gap in our knowledge. It is a sign that our current understanding of the universe is fundamentally incomplete. One of the consequences of our incomplete understanding is that we cannot describe what happened in the very earliest moments of the Big Bang, when the universe was so small, so hot, and so dense that quantum gravitational effects would have been dominant. The Planck epoch, the first 10 to the negative 43rd of a second after the Big Bang, is a complete mystery. Our physics simply does not apply there. The universe emerged from a state we cannot describe, governed by laws we do not yet know. Gravity's deepest nature, its quantum nature, is still hidden from us. There is something humbling and beautiful about this. After all the centuries of inquiry, after Newton and Einstein and Hawking and thousands of other brilliant minds working on this problem, gravity still keeps its deepest secrets. It yields knowledge slowly, reluctantly, in small pieces, as if rationing the revelations. And perhaps that is appropriate. The universe is under no obligation to be fully comprehensible. Its depths may exceed our capacity to understand. But we can keep looking, keep asking, keep listening to the data, and every now and then, gravity will give us something extraordinary, a new ripple in space-time detected by sensitive instruments, a new image of a black hole shadow captured by telescopes working together across a continent, a new confirmation that the equations we have written actually describe the real curvature of real space-time. Gravitational waves carry information that light cannot. They pass through matter almost entirely unimpeded. A gravitational wave from a neutron star merger 1,300 million light-years away passes through every star, every cloud of gas, every planet in its path, barely slowed or scattered at all. This means that gravitational wave astronomy can see things that are invisible to light, processes happening inside dense objects, events hidden behind curtains of gas and dust. The universe's most violent and compact phenomena, revealed in ripples of spacetime, rather than photons of light. The future of gravitational wave astronomy is enormously promising. A planned space-based gravitational wave observatory called LISA, the Laser Interferometer Space Antenna, would consist of 3 spacecraft flying in a triangular formation, several million kilometers apart, measuring gravitational waves with arm lengths millions of times longer than LIGOs. This would make LISA sensitive to lower frequency gravitational waves, allowing it to detect signals from merging supermassive black holes, compact binary stars in our galaxy, and possibly even remnants of gravitational waves from the very early universe. LISA would be a new kind of telescope, one that listens to the universe rather than looking at it. The Einstein telescope, a proposed next-generation ground-based gravitational wave detector in Europe, would be built underground in a triangular configuration with 10-kilometer arms, far more sensitive than current detectors. It could detect neutron star mergers across the entire observable universe and would accumulate detections at a rate that would transform our understanding of compact object populations and stellar evolution. Gravity also plays a central role in the phenomenon of cosmic inflation, the hypothetical period of extremely rapid exponential expansion that may have occurred in the first fraction of a second after the Big Bang. If inflation occurred, it would explain several otherwise puzzling features of the universe, including its extreme flatness, its uniformity on large scales, and the specific pattern of density fluctuations we see in the cosmic microwave background. Inflation requires a form of energy that behaves like an anti-gravity at very high energy densities, driving the expansion, and then decays away, leaving behind the hot, dense plasma of the early universe. The mathematical details of inflation involve general relativity applied to exotic forms of matter and energy, and the theory makes testable predictions, including the existence of a background of primordial gravitational waves, which future CMB experiments and space-based gravitational wave detectors might be able to detect. If primordial gravitational waves are detected, they would provide a direct window into physics at energy scales far beyond anything achievable in any particle accelerator. A direct observational probe of conditions in the universe when it was a tiny fraction of a second old. It would be one of the greatest observational discoveries in the history of science. Let your thoughts drift like smoke in still air, curling gently and dissipating into the dark. There is no urgency. There is nothing to hold on to, just the soft, warm, gravity-held darkness of the night. The concept of gravitational potential energy is one of the most useful in all of physics. When you lift an object, you do work against gravity, and that work is stored as gravitational potential energy. When the object falls, the potential energy is converted back to kinetic energy. In the idealized case with no friction or air resistance, the total mechanical energy, kinetic plus potential, is conserved. This conservation of energy is one of the deepest and most general principles in physics, connected by a profound mathematical theorem, due to neither to the symmetry of the laws of physics under time translation. The fact that the laws of physics are the same today as they were yesterday and will be tomorrow. Hydroelectric power is essentially gravitational potential energy made practical. Water is lifted by the sun's energy through evaporation and falls as rain in mountains. It flows downhill to reservoirs, where it is allowed to fall through turbines that convert the gravitational potential energy to electrical energy. The sun's energy lifts the water, gravity pulls it down, and we capture the falling as electricity. The energy released in a supernova explosion is predominantly gravitational in origin. When the core of a massive star collapses, the gravitational potential energy released, as the core goes from the density of ordinary stellar matter to the density of a neutron star, is about 3 × 10⁻46 joules, roughly 100 times the total energy the sun will radiate over its entire 10 billion year lifetime. Most of this energy, about 99%, is radiated away as neutrinos in the first few seconds of the collapse. The remaining 1% is enough to blow off the outer layers of the star in the brilliant explosion we call a supernova. the formation of a planet from a protoplanetary disk, also converts gravitational potential energy to heat. As material in the disk clumps together under gravity, the gravitational energy released heats the growing planetesimal. The early Earth was molten not primarily from radioactive decay, but from the heat of accretion, the gravitational energy of all the material that fell together to form the planet. The Earth's interior is still hot today, partly from the residual heat of formation, and partly from the ongoing decay of radioactive elements like uranium, thorium, and potassium-40. This internal heat drives the convection in Earth's mantle that moves the tectonic plates, builds mountains, and powers volcanoes. Gravity gave us the heat that keeps our planet geologically active and indirectly habitable. Your breathing is so slow and even now. In and out, in and out. Like the tides pulled by the moon, rhythmic and inevitable and perfectly peaceful. Let each breath be a little deeper, a little slower, a little more completely relaxing. The idea of a graviton, the hypothetical quantum particle that carries the gravitational force the way photons carry the electromagnetic force, is a central concept in attempts to build a theory of quantum gravity. If gravity is quantized like the other forces, then there should be a particle corresponding to its force-carrying field. Theoretical analysis of the properties such a particle must have, if it exists, predicts that it should be massless like the photon, so that gravity has infinite range. It should have a spin of 2, twice the spin of the photon, because gravity couples to all forms of energy and momentum rather than just electric charge. And it should travel at the speed of light, since gravity, like electromagnetism, propagates at the speed of light. The speed of gravitational propagation is not just a theoretical prediction. It was directly confirmed by the multi-messenger observation of the neutron-star merger in 2017. The gravitational wave signal and the gamma ray burst from the merger arrived within 1.7 seconds of each other, despite having traveled 130 million light-years. Given the vast distance traveled, a 1.7-second difference represents a fractional difference in speed of less than about 1 part in 10 to the 15th power. This places an extraordinarily tight constraint on any deviation of the speed of gravitational waves from the speed of light, and rules out large classes of modified gravity theories that predicted a significant difference. General relativity itself predicts that gravitational waves travel at exactly the speed of light, a consequence of the fundamental structure of the theory. The 2017 observation confirmed this to a precision far beyond what had previously been tested, directly and dramatically demonstrating the success of general relativity in describing gravitational wave propagation. The detection of gravitational waves from neutron-star mergers also has important implications for our understanding of the origin of heavy elements. Before these detections, the origin of elements heavier than iron was somewhat uncertain. Core collapse supernovae were thought to be a major source, but the details did not fully account for the observed cosmic abundances of the heaviest elements. Neutron star mergers, called kilonovae, had long been proposed as an alternative or supplementary source. The 2017 kilonova event, observed in optical and infrared light as well as in gravitational waves and gamma rays, was bright enough to spectroscopically identify rapid neutron capture, the R process, as occurring in the expanding ejecta. This was direct observational evidence that neutron star mergers are indeed factories for heavy elements including gold, platinum, and rare earth elements. The atoms of gold and platinum on Earth were forged in such violent events billions of years ago, and were spread through the universe as the ejected material mixed with the surrounding gas that eventually coalesced into our solar system. Gravity shaped not just the large-scale structure of the universe, but the very atoms from which your body is built. The heavy atoms in your body, the iron in your blood, the calcium in your bones, the gold if you are wearing any, were forged in stellar interiors and stellar explosions driven by gravity. Your atoms are stardust, and gravity is the sculptor that shaped the stars from which that dust came. There is a beautiful concept in physics called the virial theorem, which describes the relationship between the average kinetic and potential energy in a gravitationally bound system. For a system in a stable, time-averaged equilibrium, the virial theorem states that the time-averaged kinetic energy is equal to minus 1/2 times the time-averaged potential energy. This has a remarkable implication. When a gravitationally bound system like a gas cloud or a galaxy cluster loses energy, for instance by radiating heat, it does not cool down, it heats up. As energy is radiated away, the system contracts under gravity, and the potential energy released by contraction exceeds the energy lost by radiation, leaving the system hotter than before. This is why stars shine. As they radiate energy, they contract, and the gravitational energy released by contraction heats the core until nuclear fusion ignites. This negative heat capacity of gravitationally bound systems is one of the most counterintuitive things in astrophysics. It means that gravity behaves in a fundamentally different way from ordinary matter. Cool ordinary gas, and it contracts and cools further. Cool a gravitationally bound gas cloud, and it contracts and heats up. The center of a contracting gas cloud gets hotter as it radiates energy, until the temperature is high enough for nuclear burning to begin. At that point, the outward pressure of the burning gas halts the contraction, and the star enters its stable main sequence life. Let yourself drift a little deeper now. Let the concepts wash over you without effort, without needing to be grasped or held. They are just words, soft and rhythmic, and the darkness behind your closed eyes is deep and comfortable. The concept of escape velocity can be extended to the entire observable universe. The observable universe is the region from which light has had time to reach us in the 13.8 billion years since the Big Bang. It has a radius of about 46 billion light years. Beyond that horizon, there may be more universe that we simply cannot see because the light from it has not had time to reach us yet. If the universe is infinite, as many cosmological models suggest, there is an infinite amount of matter and space beyond our observable horizon. The total mass energy within the observable universe is enormous, something like 10 to the power of 53 kilograms in ordinary matter alone, plus roughly 6 times that in dark matter, plus about 17 times that in dark energy equivalent. The gravitational effects of all this mass energy are what shape the geometry of the observable universe, determining whether it is positively curved like a sphere, negatively curved like a saddle, or flat. Current observations suggest that the universe is very close to flat, to within about 0.4%, meaning that the total energy density is very close to the critical density needed for a flat universe. The anthropic principle in its weak form notes that the laws of physics and the constants of nature, including the strength of gravity, appear to be fine-tuned for the existence of complex structures and life. The gravitational constant g, which determines the strength of gravity, must lie within a certain range for stars to form and burn long enough for planetary systems to develop and for life to have time to evolve. If gravity were much stronger, stars would burn their fuel much more quickly and would be far too short-lived for life to have time to evolve on any orbiting planet. If gravity were much weaker, gas clouds might not collapse at all to form stars, or stars would be much less massive and much dimmer. Similar fine-tuning arguments apply to other constants of nature. The strong nuclear force determines the rate of nuclear burning in stars. The electromagnetic force determines the chemistry of living things. The cosmological constant, or dark energy, must be very small compared to the values particle physics would naively predict in order for the universe to have the structure we observe rather than collapsing or flying apart almost instantly. After the Big Bang, these apparent fine-tunings have led some physicists and philosophers to invoke the anthropic principle as an explanation. We observe the constants to have the values they have because if they had other values, we would not exist to observe them. In an infinite or very large multiverse, regions with different values of the constants might exist, and we necessarily find ourselves in a region hospitable to our existence. This is a controversial and philosophically contested argument, neither universally accepted nor universally rejected, but it speaks to the deep interrelatedness of gravity, the other forces, and the conditions for complexity and life. The night is very deep and quiet now. The room around you is still. Outside, the Earth is turning slowly under the stars, held in its orbit by the sun's gravity, and the moon is riding its own orbital path, pulled by Earth's gravity. And the stars are moving in their slow galactic orbits around the distant center of the Milky Way, all of it bound together in a vast, quiet, gravity-held dance that has been going on for billions of years and will continue for billions more. You are part of it. This small, warm, breathing thing resting on the surface of a small rocky planet orbiting an average star in the outer reaches of an ordinary spiral galaxy, in a cluster of galaxies that is itself part of a vast cosmic superstructure. You are tiny, and you are part of something enormous, and gravity is the thread that connects the two. The force of gravity between you and the Earth right now is your weight. If you weigh 70 kilograms on Earth, the gravitational force pulling you toward the Earth's center is about 686 newtons. The gravitational force pulling the Earth toward you is also exactly 686 newtons by Newton's third law, but the Earth, being vastly more massive, barely responds. You feel the force entirely. You are the one who stays in place or falls, not the Earth, and yet the force is mutual. You pull the Earth toward you just as it pulls you toward it. You have gravity. You curve space-time. Not much, not measurably in any practical sense, but truly and really and according to the exact same equations that describe the gravity of stars and black holes. Everything that has mass participates in gravity. Everything contributes to the curvature of space-time. Everything is connected to everything else by this force, across any distance, however vast. There are no exceptions. The force becomes fantastically small with distance, but it never becomes zero. In that sense, you are gravitationally connected to the farthest galaxy we can observe, UHZ-1 or GNZ-11, or whatever the most distant detected object may be, billions of light-years away. Your gravity reaches there, right now, vanishingly small but present, and its gravity reaches you. The universe is not a collection of isolated things floating in an empty void. It is a web of gravitational connections, a fabric of interrelated curvatures, every piece of matter influencing every other piece, all the way across the cosmic horizon. There is something quietly comforting about that, even in its enormity. You are not alone. You are woven into the fabric of the universe by the oldest and most universal of forces. Every heartbeat, every breath, every movement you make ever so slightly shifts the curvature of space-time in your vicinity, sends a tiny ripple, infinitesimally small, outward at the speed of light across the universe. You leave a gravitational mark on the universe with every moment of your existence, and the universe holds you in return. Let that knowledge be the last thing you carry into sleep. You are held. The universe knows you are here. Gravity keeps you close to this small, warm world, and this world is the right place for you to be right now. and sleep is the right thing for you to be doing. And everything is exactly as it should be, and all you need to do is let go, and breathe and sleep and rest and be held, gently and completely and without condition by gravity, by the earth, by the night, by the universe itself. Breathe in and out, slower, softer, quieter. The words are fading now, becoming just a murmur, just a sound, just the rhythm of rest. Let your mind go blank and peaceful. Let the darkness be soft and deep and welcoming. Let sleep come to you now as naturally and inevitably as an object falling under gravity, falling and falling in perfect silence through the dark and quiet universe, falling into rest, into sleep, into the warm and gravity-cradled stillness that is waiting for you, that has always been waiting for you, that is yours. Sleep now, deeply, peacefully, completely. Good night. But the story of gravity is also the story of human curiosity, of the irresistible compulsion to look at the world and ask why, to refuse to accept mystery as a final answer, to reach for understanding even when the understanding is difficult and strange. Tycho Brahe spent decades making meticulous observations of planetary positions with instruments of his own design, before telescopes existed, accumulating the most precise astronomical data the world had yet seen. Johannes Kepler used that data, after Brahe's death, to discover his 3 laws of planetary motion. Newton used Kepler's laws as a starting point for his theory of universal gravitation. Leverrier used Newton's theory to predict the existence and position of Neptune, which was then found by telescope within 1 degree of the predicted position. One of the greatest triumphs of theoretical physics. Einstein used the anomalous precession of Mercury's perihelion, which Newton's theory could not explain, as one of the clues that led him toward general relativity. Eddington tested Einstein's theory during the 1919 eclipse. LIGO detected the gravitational waves Einstein predicted a century before. Every step built on the last, across generations, across cultures, across centuries, the slow accumulation of understanding about this force that holds everything together. That chain of inquiry is still unbroken. Physicists today are working on the next step, on quantum gravity and the unification of the forces, on dark matter and dark energy, on the physics of the Planck epoch, on the nature of the singularities inside black holes. They do not know what they will find. Perhaps they will discover that spacetime is not continuous but quantized at the Planck scale. Perhaps they will find that extra dimensions exist and that gravity leaks into them. Perhaps they will discover something entirely unexpected, something that will require an entirely new conceptual framework. The way Einstein's spacetime required a new conceptual framework beyond Newton's absolute space and time. Whatever they find, it will almost certainly be strange and beautiful and surprising, because that is what the universe has always been, at every level of depth at which it has been examined. You are the inheritor of all of that understanding. Lying here in the dark, held by gravity, you carry within your mind the fruit of thousands of years of human inquiry into the nature of this force. From Aristotle's heavy objects seeking their natural place, to Newton's mathematical harmony of the spheres, to Einstein's curved and flexible spacetime, to LIGO's impossible measurement of a spacetime ripple smaller than an atomic nucleus. The story of gravity is also the story of humanity's growing awareness of its place in the universe, of the scale and age and grandeur of the cosmos, and of the subtle, deep, mathematical laws that govern it all. And now it is time to let that story rest for the night, to let the mind that holds it rest, to let the body that carries that mind rest. Held safe and warm, and still by the very force that is the subject of the story. Sleep now and dream whatever you dream, and know that when you wake, the universe will still be there, still expanding, still evolving, still full of unanswered questions and undiscovered wonders. And gravity will still be doing what gravity has always done, patient and tireless and universal, holding everything together, holding you, holding the world until morning. Good night. There are approximately 300 billion stars in the Milky Way galaxy, and every single one of them is held in the galaxy by gravity. Every one of them is a gravity-powered furnace, converting the gravitational collapse of gas into the heat and pressure that ignites nuclear fusion, shining for millions or billions of years until the fuel runs out and gravity collapses them once more. The galaxy itself orbits its center under the influence of gravity, completing one revolution in about 225 million years, an interval sometimes called a cosmic year or galactic year. Since the Earth formed, it has completed about 20 cosmic years. Since the first complex animals appeared, about half a cosmic year has passed. Since the dinosaurs went extinct, less than 3% of a cosmic year has elapsed. On the scale of cosmic time, you are a brief flicker. On the scale of a human life, the night is short. And on the scale of this moment, this quiet dark bedroom, this slow breath, this heavy and comfortable and utterly at rest body, the whole universe is simply a story playing softly in the background. And it is time to stop listening to it and to sleep. Sleep. The gravitational waves that LIGO detects arrive from events so distant that the light from those events has been traveling for hundreds of millions or even billions of years. When the two black holes whose merger was detected in September 2015 came together in their final collision, the Earth was in the Cretaceous period. Dinosaurs had not yet appeared. And the ancestors of all living things were single-celled organisms floating in shallow seas. The ripple those merging black holes sent out traveled through billions of light-years of space, passing through galaxies, through clouds of gas and dust, through the void between galaxy clusters, until at last it arrived at a small blue planet orbiting an unremarkable star, and was caught by human instruments tuned to listen for exactly this kind of whisper from the deep universe. This is one of the great achievements of human civilization. This is what curiosity and persistence and mathematics and engineering can accomplish. We built ears sensitive enough to hear the universe speak, and the universe spoke, and we heard it. Let that be enough for tonight. Let that be the last thought. The universe speaks. We listen. And now we rest, held in the quiet, held by gravity, held by the night. Sleep well.